Good afternoon, everyone. My name is Jack Hao. Today, I will present my capstone project, a web GPU-based geographic information system. This project explores how a browser-native system can combine 3D GIS visualization, streaming spatial data, and the dashboard analytics in one interface. Today, I will briefly cover the problem, the motivation, and the research gap, the system design, the data pipeline, the experimental results, and then I will spend the last part on a live demo. First, the problem. In many browser GIS workflows, the map view, the dashboard, and the analysis tools are still separated. When datasets become large, browser interaction can become less responsive, and the user often need to switch back and forth between spatial view and statistical view. So the goal of this project is to build one browser-native platform that combines 3D GIS rendering and analytics, uses web GPU for real-time rendering of large building datasets, and keeps the design extensible for future AI-assisted analysis. The core question is, can a unified web GPU-based platform make WebGIS more interactive, scalable, and usable? This project matters for three reasons. First, WebGPU provides a more modern and explicit GPU programming model for browser rendering. Second, real estate and urban analysis benefit when maps and analytics are kept in one coordinate interface. Third, this project can survive as a reference architecture for future browser GIS and AI assistant tools. The three main contributions are number one, a unified web GPU GIS plus dashboard. Number two, a streaming pipeline using H3 and NDJSON. And number three, an extensible AI chat layout prototype. This project focuses mainly on architecture, interaction, and implementation feasibility, rather than a full production-grade GIS platform. When I review prior work, I found that different research lines each do something well, but still leave a gap. GPU-centric GIS research is strong in rendering performance, but it is often desktop-oriented. WebGL and web-based 3D visualization are accessible in the browser, but they are still face performance and flexibility constraints for dense 3D scenes. WebGIS dashboards are useful for coordinated decision support, but they are often not GPU first, and they are rarely unified with real-time 3D rendering. So the gap addressed here is a browser-native architecture that combines web GPU rendering, structured spatial streaming, and synchronized analytics in one interface. This slide shows the overall pipeline. The data starts from OpenStreetMap and the GeoFabric extracts. Then I preprocess the data using tools such as GDAL, GeoJSON conversion, and AirCAD tessellation. The processed data is stored as H3 indexed NDJSON tails. At runtime, a Node.js plus WebSocket backend streams visible region data to the client. On the front end, Web GPU and WASL render the geometry, and the interface support synchronized data board interaction, layout switching, bird's eye rotation, zoom-dependent transitions, and hover picking. An important design goal here is to keep loading responsive, so the system uses central first delivery and incremental GPU deployment to avoid US stale. So this is the main working layout of the system. On the left side, there are KPI cards. On the top right, there are charts. And the main web GPU canvas render building at multiple scales. As the user changes zoom level and navigates the map, the dashboard remains synchronized with the spatial wheel. So this layout demonstrates the core value of the project. keeping visualization and analytics together in one coordinate interface instead of separating them into different tools. The second layout is an AI chat prototype. At the moment, this page is static only, and it is not connected to a live OpenAI workflow or backend chat pipeline yet. Its purpose is to show how this platform could evolve from a dashboard-driven GIS system into an AI-assisted geographic analytics interface in the future. So here, the contribution is mainly about extensibility and the future direction rather than a complete AI feature. On the front end, I use JavaScript ES module, the Web GPU, WGSL, Geometrics, and the ChartJS. On the backend, I use Node.js, the WebSocket server, and the NDJSON tail streaming. And I will skip the interaction because I already talked about this part. So these slides focus on the data pipeline. I start from OSM regional extract, inspect and convert them with QGIS and GDAL tessellate polygons into triangle mesh with air cut, partition the result into H3 tails and store them as NDJSON fields. At runtime, the server receives a visible region request, compute intersect H3 cells, sort tails by distance to the viewpoint center, and streams them through WebSocket. On the client side, received features are not uploaded to the GPU all at once. Instead, they are stored in a pool sorted near to far and deployed incrementally under a time budget. This design helps avoid freezing the browser and improves the perceived responsiveness. For evaluation, I use Seattle area OpenStreetMap building data, a Node.js preprocessing pipeline, air-cut triangulation, H3 partitioning, and JSON tail storage, and Web GPU-enabled browser with a WebSocket backend. The system was tested with increasing number of building and interactive navigation include far to near scenes transitions. In the current prototype, the system can render more than 100,000 buildings interactively. During testing, the observed resource profile was about 6% CPU, 20 to 30% GPU, and around 600 megabytes of memory usage. This result suggests that the shared GPU buffer, batching draw costs, incremental streaming, and visible region loading are effective in keeping the interface responsive during zoom and pan. So even though this is still a prototype, the performance results support this feasibility of the architecture. The key findings are: first, GPU-first rendering can significantly improve browser-side GIS responsiveness. Second, spatial preprocessing and H3 tails reducing transfer and memory overheat. Third, NDJSON plus WebSocket streaming makes large dataset more feasible to explore incrementally. And fourth, synchronize the map and dashboard create a better exploratory workflow than fragment tools. And there are still several limitations. The current system focuses mainly on building geometry rather than full GIS layers. The dashboard value are static demo values rather than live market analysis. The AI chat view is currently static and not connected to the live model, and some pipeline constraints are still hard-coded for experimental. With that, I would like to move to the live demo. In the demo, I will briefly show the main GIS layout, interactive navigation, streaming behavior, dashboard, synchronize, and the layout switch to the AI prototype page. So let me show. So here you can see it's running on a browser, and here is the main dashboard, the centric GIS layout. And let me click start. and you can see the building is loading. As I zoom in and zoom in, the map scale change, and you can see the ground and dashboard remains synchronized, and you can see the sky, and you can go back. You can see the building is still loading, and when I zoom out, the system streams visible region data through WebSocket instead of loading everything at once. And buildings are deployed incrementally to the GPU to keep the interface responsive. And here I switch to the second layout, which is AI chat prototype. So you can see I can draw the data, sorry, I can draw the data to here, and you can see the visual effect, and you can ask what is this? Uh, and it will say no, not before payment because it did not connect to the some AI API yet, but we can still like trying to use it, trying to upload some something like that. Uh, yeah, so and you can see the animation here. So yeah, so I think that's all for my presentation, and here is my key reference, and thank you very much.
Hey, thank you for the presentation. Do we have any questions for Rauji? Okay. I'd like to ask you one question. So, you mentioned on the layout too, you'll
Yeah.
have the AI assisted geographical suggestions, right? So,
Yeah.
do we have any like system or any preferences set as of now to see if there's any AI hallucination or drift happening? How do we manage that kind of a scenario? Or it's just something which has been implemented on a very baseline scale as of now?
Because the capstone is a focus of the this version was on the
Mm-hmm.
browser GS architecture, rendering pipeline, and the streaming workflow. So for the AI page, which means the layout second, I intentionally keep it as a prototype layout to show future extensibility rather than treating API integration as the main contribution. Uh, so
Got it, got it.
yeah, so basically, if let me share it. If it connect to AI API like OpenAI API, it can obviously based on the topic like the map and the price of the renter price and total price or something more in the future. And I just want to showcase my technique and experience by using this opportunity and this capstone. Yeah.
Yeah, got it. So it works on a very baseline level now, but this has a potential to like dive into some, fine-tune modeling and AI drift management system, but that's something which can be considered under the future scope, right?
Yeah.
But yeah, this looks great. Thanks a lot for your presentation.
Thank you very much.
Okay, so we can move on to our next presentation for today. Is it Rajesh for this the second participant? Because I have a
Yeah,
different schedule.
yeah, it's me, it's me.
Okay, okay. Yeah, please, you can start the presentation.
Yep, sure. So I'm sharing my screen here.
Any issues, Rajesh?
Yeah, just a minute. Uh, it- Sorry for the disturbance, but share my screen. So I need to start from the beginning, right? This is the good icon. I need to select
Y-
Namrata.
Yeah, yeah.
Yeah. So, hello class. My name is Rajesh. Today I'm presenting my project, Auto Chain, uh, uh, agentic AI driven in inventory and supply chain intelligence systems. So, where I'm presenting today and going to my next slide. This is the all the topics which I am covering today, and so going to my next slide. So motivation. Nowadays, adaptive demand forecast using multi-agents reinforcement learning. So so uh, so in these days. So hello, hello, number.
Yeah, yeah. We can hear you, but your
So
slide presentation stopped, so we can't
it
see your
stopped.
screen. Yeah.
Oh
Can you try sharing again?
yeah, I'm trying to share, but just a
Yeah, yeah.
minute. I'm
We could see your presentation. Just like 2 seconds back, the screen share stopped.
so is it coming right now?
No, right now we can't see it.
So just a minute. So it's something technical. I think network issue is going on. Just a minute. So can I reconnect to Namrata if there any chance if someone.
Yeah, I think Gaurav, are you ready to present now? We can take you
Yeah,
off first, and then until then Rajesh can figure out his technical issues. Then he can join back.
yeah, I'm ready.
Okay, so Rajesh, we you have 20 minutes until Gaurav Reddy completes his presentation. So hopefully we'll have you back on the call then.
Sure, Namrata. Thank you.
Okay, no
Yeah,
worries.
it's visible.
Yeah, yeah, we can see your screen.
Hi, hello everyone. My name is Guru Reddy. Today I am going to present my capstone project. It's AI-based smart queue and appointment management system. The main goal is reduce waiting time and improve service efficiency using machine learning and explainable AI. This is the main goal. This is the main goal of my project. Like traditional systems only react after problems occurs, but the system predicts issues in advance. It combines data analysis, machine learning, and real-time decision making into one platform. And in this presentation, I will first explain why this is problem is important. Then I will define the problem and discuss background research. After that, I will explain how my system works, including implementation, design, and finally, I'll show the results and conclusion. This is my motivation. Like in real world services systems like hospitals, banks, and offices, long waiting times are the major issues. Customers often become frustrated due to the delays or lack of transparency. And another major problem is no shows, where customer missing appointments, wasting time and resources. The existing system do not use data efficiency to solve this problem. So this is my motivation to use AI and to make smarter decisions and improve overall efficiency.
And that problem, this is my problem statement. The key problem is the current queue and the appointment systems are static and non-adaptive. They cannot predict future delays or adjust schedule dynamically. Handle both walk-ins customers and schedule appointments create complexity. No shows and uneven demand lead to inefficiency use of staff and resources. So there is need for the intelligent systems that can predict and adapt to the optimizing operations. Like appointment scheduling, this is my background. Appointment scheduling has been widely studied, especially in the healthcare system. Machine learning is now being used to the predict patterns like no-shows and waiting times. Then Q theory helps to uh, Q theory provides mathematical models to understand the delays or delays, and real-time dashboard helps administration to monitor the system performance. They can if they want it, they can adjust from the admin dashboard. And these concepts together from the foundation build an intelligent queue system. Previous research has explored different aspects of this problem. Some studies focuses on predict no-show using machine learning models. Others focus on optimizing schedule using real-time data. There are also systems that use dashboards for the monitoring. However, most of these solutions address only one one part of the problem, not complete system. Uh, by using this project, I think we can fill those gaps. This is my synthesizes matrix. Well, here we can see the previously there are some uses the machine learning to predict the no-show rates, and some other projects are the AI-based optimizing schedule. But we are combining both machine learning and explainable AI to reduce the waiting time and delay. And my current features, this system provides like a online appointment booking for the user-friendly interface and a real-time monitoring for the administration and staff. And while you're booking the appointment, it can predict the waiting time and no-show rate. Admin dashboard can show the queue length and appointment status. By using explainable AI like shape and line methods, it can be the transparency like. And for the futures, we can build a mobile application, and we can send the real-time notifications to the user, and dynamically we can allocate the staff to according to the peak hours or everything. We can build a AI chatbot for the appointment schedule assistance for the user. These are my future features. Approach. First, we need to collect the data. For this project, I collected the data from the AI like synthetic data set due to the privacy issues. So after collecting the data set, we need to pre-process the data set, and we need to analyze the patterns in waiting time and no-show behavior. Then we need to train our machine learning models and apply the explainable AI techniques to model transparency. And finally, these models are integrated into the system for real-time use. And this is my solution architecture. In this, first we can see the user layer. In this, we have a two dashboards, like user dashboard and admin dashboard. In user dashboard, you can appoint the, you can schedule an appointment, or if you want, you can reschedule an appointment also. For admin dashboard, uh, we can schedule the walk-in appointments, or we can monitor the queue length and waiting time and everything. In this application layer, After scheduling an appointment, we can see the what's the waiting time and no show rate, and with the help of AI, explainable AI like Shame and Lime. In data layer, uh, we use the data sets to train the machine learning models, and we are storing the real-time data in the MySQL MySQL scheme. This is my UI design for the admin dashboard. It's like a user can easily navigate and book appointments. Admin have a dashboard showing real-time queue information. Charts and graphs helps visualize the trends like waiting time and demand. Um, and Next, the implementation. The implementation uses the Python for the backend Python for the backend development using machine learning libraries, and data processing and performed using pandas and NumPy tools. And we train the random forest models for the waiting time and no-show prediction. Backend build using fast APIs with prediction endpoints. Front-end dashboards displays the result to users and user and admin. Here, I already mentioned that I use a synthetic data set, which is generated by AI. And in the data set, we have a 15,000 visiting services and 30 operational behavior features like queue length and staff availability, no-show rate, and timestamps and everything. Here is my correlational matrix. You can see the exams relation between the key numerical variables. It helps identify which variables influence the waiting time. For example, queue length and backlogs are positively related to the waiting time, and staff availability may reduce waiting time. This analysis uses for the future selection in the machine learning model. And I can show you the live demo. Uh, after After this, these are the findings here. Uh, Waiting times depends on the multi-factors, not just a staff count. Peak hours significantly impact congestion, and the service history is important for the prediction no-show rates. And explainable AI helps understanding these patterns clearly, like why, how much it's waiting time, like um, what are the main points here, important features to predict, like to show the waiting time. Hmm. And these are the results. I use a random forest. It get model achieve more accuracy. It performs better than the logistic regression. The model can predict both waiting time and no shows efficiently. Important features including queue length and previous no shows. This result shows the system in the reliable and useful. And the conclusion, the system improves queue management using AI. It helps reduce waiting times and improve efficiency. It supports better decision making using data insights. Explainable AI builds trust in the system overall. It provides smart and practical solutions. For the future works, it can be for the next, we can use the real-time data to improve more accuracy. Real-time data integrity make it more dynamically. And here I want to show the It's taking time. Here, here we can register. It's a, like a here we can register for. We can register. Here we can access from the user or admin. This is the user. Register successfully. User 11. Here we can book an appointment. Phone number. And we can prefer like what time we can prefer and what the radius for the what's the distance between your appointment like service and you for your destination and the urgency. Here you can see the token one. Like waiting time is 8.23 minutes and no show probability will be the 7.3 percentage. No show factors take most time like while you are predicting the probability. This is the like booking lead hours will be the main priority. It takes from there and then it can turn into the probability. For waiting factor, it like location ID and service ID will be the and we can this is the admin dashboard. Total appointments for today. The waiting time, average waiting time is 7 minutes. And here we can book the appointment, like walk in. Here we can see the position and token number, waiting name, and no-show probability. Here we can see the waiting time. Here we can access the counter, like based on the flow, we can activate and deactivate our counters. And here is the walking. Here we can
Sorry to interrupt, Gaurav Reddy. We
yeah,
are actually over time by 2 minutes. We have three
yeah, it's
minutes
done.
for the Q&A. So you can take a couple of seconds to wrap up the demo, and we'll have
Yeah,
3 minutes for
it's almost
questions.
done. It's almost done.
Yeah. Okay.
Yeah,
Sure.
yeah. If you have any doubts,
Yeah. Do we
I'm
have any
gonna.
questions? Michael?
No, I have no questions. Thank you.
Okay. Uh, I think I'm interested in one particular question here, because I was trying to understand how have you integrated the the information regarding the doctors. I remember you mentioning that it is a synthesized data which you created using AI.
Yeah,
But if we expand this prototype into like a live project, I'm just trying to understand, like since we have a lot of compliance rules out there, like HIPAA compliance rule and so on,
mm.
how do you plan on getting the hospital site data along with patient data? Because that's something which can be a big blocker in terms of having
Yeah.
this
That's the
project
main
going.
issue. Yeah, that's why we use the synthetic data set right now. I don't know how we can access the real-time data. Like it's a it's a main issue. It's like a privacy for the patient information. So we need to figure it out how we are going to, like, we need to bill separately for those services which can be stored on those databases.
Okay, so you are kind of suggesting to have this model based on like a separate database altogether and
Yeah,
not having a generalized project for all the hospitals.
yeah.
Okay, yeah, thank you for answering the question and thank you for the presentation.
Yeah, and
Thank
I
you.
think Namrata, if I may step in there, right? Essentially, when it comes to all these patient registration systems, there are multiple hospital systems that are in play here. They don't, only some of them are facilities that will be willing to share data across each of those facilities. So I think I get your point in terms of, like, is there some level of collaboration? I think that I'm sure that we should have one, but there is also this aspect where one facility will not deliberately share with other facility because of a specific reason. They could be competitors with each other, and as we see very clearly in the industry today, within the hospital industry today. Thank you.
Yeah,
Thank you.
thank you for stepping in. Um, so we have a last presentation for today. Rajesh, if you're ready, we can start with your presentation. I hope you we are cleared out with the technical issues you had.
Yes, Namrata, thank you for waiting.
Yeah, no worries. We can start with yours now.
Yeah, I'm sharing my screen right now. So, hello class. Today I'm presenting my project Auto Chain. So, agentic AI driven inventory and supply chain intelligence system. So my project builds an intelligence system that help organizations predict demand, manage inventory, and handling supply risk. So going to my next slide. Yeah, going to my next slide. So these are all the uh, parts I'm covering today in my presentation. So going to my motivation section. The motivation behind my projects comes from both research and real world supply challenges. So research shows that smart forecasting methods can adjust quickly when demand changes. So modern supply chains are becoming more complex due to changing customer demands and supply delays and unexpected disruption. So most research solves only one part of the problem, but very few systems integrate forecasting, inventory, and supply decisions together. So these gaps is what auto chain aims to address. And going to my next slide, problem statement. The main problem is that traditional supply chain systems uses fixed rules and manual decisions making. So someone need to order stock. So these often leads to stock outages, overstocking, or reliance on a few suppliers. So these systems suggest when demand suddenly increases or when suppliers delay shipments. So the system also do not adapt in real time to demand changes or supplier delays. So this leads too much or too less inventory, uh, little inventory. So forecasting, inventory management, and supply decisions are used separately process. So this problem is the lack of an integrated intelligent decision systems. So going to my next slide, background. Supply chain today generates massive amount of operational data, includes sales and supplier performance information. So machine learning has improved forecasting accuracy uh, by learning from data. So agent-based AI goes on a step further by enabling automation decisions making. So although Researchers show that machine learning and agentic AI based AI can implement adaptability in most existing systems. So these futures work separately rather than working together in real time. So going to my future here, synthesis matrix in demand prediction, different studies treat forecast different ways. Like Chen 2026 focus on multi-agent reinforcement learning for forecasting, while CU in E25 trust demand only as an input. So few studies combine demand prediction with uh, operational decision making. So these essential articles applies AI agents to solve specific problems such as forecasting or supplier coordination. Going to my next slide. These are all my future current future list. So firstly, demand forecast. So linear regression capture stable and overall demand trends, while random forest capture complex and irregular patterns such as sudden demand changes or variability across products. So coming to my next future here, inventory monitoring and rolling decisions, future explanation. So this future continuously track inventory levels in real time. Uh, Whenever there is a sales or low updates, the systems recalculate when to reorder and how much to order. Uh, this helps reduce stocking outage, running out of stock, and overstocking extra inventory. So MPC based approach. The system uses Model Context Protocol (MCP) for continuous decision making. It continuously monitor inventory changes. So coming to my third future. Supplier reliable scoring. So the systems evaluate supplier based on the past deliveries performance. Reliable suppliers are performed, while risky suppliers are given low priority. The system also distributes reorder across multiple suppliers to reduce supply risk. Coming to my next future, uh, uh, regional and promotion analysis shows how demand charges across regions and promotions. Going to my next slide, approach section. The systems begins by cleaning and preparing supply chains data. Machine learning models forecast future products demands. Forecast results are used to identify inventory reordering decision. Supplier performance is analyzed using reliable scoring. Going to my solution architect slide, and the system uses modular agent-based architecture. The systems collected sales, inventory, and supplier data, process it, and use machine learning models to forecast product demands. So based on the forecast, AI agents monitor inventory evaluation, supplier reliability, and generate reorder decisions and displays insights through an dashboard. So going to my next slide, ER diagram. So the dataset includes a main table called daily operations, that stores daily sales and inventory data along with the product warehouse, suppliers, and regional information. So this table has analyze product demand, track suppliers, performance, and understanding inventory decisions across different locations. Going to my UI design slide here, a reason-based integrated dashboard allows users to upload dataset, run ML demand forecasting, and select forecast prediction. These dashboards displays SKU forecast to demand products and KPI metrics such as total SUKs, uh, average, minimum, and maximum prediction demands. This is my UI dashboard and future too. I can show it in a demo section in the last. And in implementation section, the system is developed by using Python, Flask, and machine learning libraries. By building the forecast pipeline, machine learning models are built using skitlearn and pandas, linear regression, and random forest. Predict demands. Forecast results are stored in SQLite database. Going to my next slide here, data collection. The study uses a structured supply chain data set from Kaggle, contains daily operational data such as sales, inventory, supplies, and regional information. The data includes 91,250 records covering 1 year, 2024, across multiple SKUs, warehouse, supply, and region. Going to my next slide. Uh, So the data includes daily sales and inventory reorder for 50 products across multiple warehouses and regions. Demand is evenly distributed across products and regions with no single product domi dominating total sales. Going for my next slide, forecasting and my model performance evaluation. The machine learning models and linear regression and random uh, forest were tested to forecast product demands. The model achieves low prediction error, MAE 2.17, RMSE 2.73, which an R square score of 0.76, showing good forecasting accuracy. Going for my findings and results, the forecast model achieves good accuracy R square, that is 0.80, which low prediction error makes it reliable for demand forecast. Going to my conclusion section, the projects demonstrate how AI can improve supply chain decision making, demand forecast, provide reliable short-term prediction, inventory, and agents generation precision order. So going to my the next slide. So going to my the demo part here. Coming to my demo part. Yeah, this is my UI design. So here I can set the forecast horizon for 30 days. So I selected 15 days before the call joins, because it takes 2 to 5 minutes of time. I don't want to waste you guys time because I did it previously. So I run my forecast for 15 days. So this is the MAE and RMS scores. So depending on the score, it will select the model. So here it is selected as linear regression, and this is a forecast of the 15 days. So I have chosen 15 days here. So as we can see, the 15 days forecast for each product. So SUK1 to SUK day 15. So we have 50 products. So it will show the forecast to all the 50 products. So coming to my just a minute. Coming to my next so coming to my next feature here, inventory. So for forecast decision, so and the simulation decision. So it will check it will see the forecast of the 14 days. So it will see the forecast for the next 14 days, and it will check the current warehouse stock. And I choose here 14 days for the next 14 days reordering stock. So it will check the present stock and the future stock, and it will predict the future stock to order. So you can see here the reorder decision. Uh, so if it is low, so it will predict with the quantity and with the inventory. So going for my next feature here. So this is my supplier scoring. According to the score, the orders will be distributed in the regions. So it shows the four warehouses, four region stock, and the promotion uplift. So here we can see when the promotion happen, like when we run the promotion, it goes for the 26.42 units, and without promotion it you can see has a 19.50. So we have an uplift of 34.48.
Have a question, Rajesh.
Yeah.
So
Yes, sir.
when there is a situation in this case where the stock is running low and you'll have to basically reorder, what happens? How does it dynamically route it to the right supplier? A. Question B, what if no supplier has the required quantity? How does your application handle it? Thank you.
So yeah, I will show you here. So technically, for the answer for the second question, so it will checks. We have 10 suppliers here. So we are not depending on the one supplier. We have 10 suppliers. So according to that, it will check the customer. Uh, the system split the order according multiple suppliers, or triggers a partial reorder based on the available stock for the second question. And for the first question, the system checks supplier reliability scoring and availability, then automatically select the best supplier or split the order across multiple suppliers to reduce the risk.
So I'm sorry. Thank you for answering the question. One corner case is when no supplier has any quantity left because it's fast depleted across the entire supply chain. What happens in that case if a stock reordering needs to happen, but there is no supplier that can provide that SKU or SKU? How does your system handle it?
So the system mark it as an supplier risk, and risk an alert to instead of placing a normal reordering. So so it can reorder emergency actions like back ordering or temporary staff stock usages. Uh, yeah, I think so. So some part of it we need to work for the future implementations.
Got it. Thank you. Appreciate
Yeah.
it.
Yeah. Yeah. Any doubts?
No, I have no further questions, Rajesh. Back to Namrata.
Thank you.
Yeah. Yeah, thank you for the presentation, Rajesh.
Yeah. Thank you, Namrata, for hosting. Anything
Yeah,
else?
yeah, I was just checking on if we have any more questions, or else we are good to wrap up for today.
I have no questions. I'm good. Good presentation though.
Yeah. Thank
Yeah.
you.
Yeah, so I just want to thank all the three participants for your presentation and for all the questions as well. I hope you all have a good evening, and
Yeah.
yeah, you're good to wrap up the call.
Thank you, Gurva Reddy, and thank you, Rajesh.
Thank you.
And thank you,
Thank you,
everybody.
sir.
Bye.
Yeah.
Yeah.
Thank you,
Thank
Namrata.
you all. See you again.
Yeah,
Thank you.
thank
Good.
you.
Bye bye.